Okay, morning guys. It's morning outside. I guess not many people is not able to make it to the campus. Okay, so let's continue on the state variable method. So we're gonna finish this today. Okay, just quick review. State variable method, that's essentially a different way of modeling the system, a different way of analyzing the system. And the whole objective is, given a plant, okay, the plant may be represented by a transfer function, or maybe it's represented by ordinary differential equation. So what we want is, we wanted to transform that into a state space model, basically, right? We're dealing with discrete systems, so our state space model for the discrete system, it's in general the format is x over k plus 1 equal to a x of k plus bu of k and y of k equal to c x of k plus d u of k. So this is in general what we're talking about here. So this is what we call the state space equation, right? Okay, or state space model. So at this stage, what you need to know is, okay, you need to know what each one of them represents. This x of k out here, which is a vector, okay, so it's a vector of a so-called state variable, right? So this is a state variable. It's a vector. Okay. Yeah. How many state variable it is? In general, this state variable will be the number is the same as the order of the system. Okay. So maybe it's n by 1, and n it would be the order of the system. And the u is the system input. Okay. We use a vector here, basically meaning we could have multiple input to the system. Right? If your system is single input, single output, then there's just no vector, just a u of k at here, which is what we're going to deal with in this class. Okay. Yeah. And once you have the state variable now, then you can have this output, which is system output here. So the y is the system output. So the output of the system, okay, is related to the input of the system by a matrix C at here, and maybe you could also have a D here, but usually the D vector here is 0 at here. Okay, yeah. So when you have a forward term, then you have a D. Okay. So this is the state space model. So one system, okay, one system can have infinite number of state space model, and that all depends on how you select this state variable vector, okay, state variables. So we're going to show you some examples to see how many state space model you can get just based on one system equation, right? Okay. So how do we obtain this state space model of the plant or the system, right? Discrete ones. And I showed you this diagram in the previous lecture. Okay. So starting from the continuous system, which is in the ODE probably, continuous system in time domain. So you can either go through either branches here to end up with this discrete state space model. So you take a transfer function, right? From the transfer function, you discretize that. There are different ways of discretizing that, but if it's a plant, okay, most probably we're going to discretize that considering there is a zero-order hold in front of the plant, right? Yeah. So then you get a z transfer function, which is what we call pulse transfer function. Okay. Yeah. So from the pulse transfer function, you can either directly get a discrete state model, or you transform that into a difference equation, from difference equation into a discrete model. Right. So this either way is good. So in the previous lecture, we had two examples, okay, showing these two different ways of getting a discrete space model. Right. So for example, this example here, okay. So this example shows is giving a difference equation, okay, then how would you pick the state space model? Eventually, how would you end up with the state space equation, right? That example, take a look at lecture notes, okay? Yeah. So, but bearing in mind, the way to pick state space variables, okay, the state variables is not unique, okay? This is just one way of picking state variables here, right? Yeah. And the other way is from Z to the difference model. And we had another example after this one here. So giving a pulse trans function, okay, giving the pulse trans function, here's one way of deriving this state space equation. Okay, so this is what we in this particular case, it's called a nested programming. Okay, and I mentioned that this nested programming gave us a so-called observable canonical form. Okay, so which is today I'm going to talk about what that kind of form is. But okay, in short, it gives you sort of a approach at here. How do you come up with the two state variables at here? All right, yeah. So physically, what does this state variable represent in here? We actually, sometimes we actually don't really know, right? In this case, maybe it's okay because y of z is x of z. So x of z probably just output representing, okay? What exactly is x2 of z? Okay, physically, sometimes it doesn't represent any physical meanings, okay? It's just a mathematical quantity or variable. Okay, so and this approach right here, okay, this approach is what we're going to talk about in the next lecture here, okay, this is the next lecture. So how do we get a zero-order Hall equivalent discrete space model, okay, by discretizing a continuous state space model? Okay, so this is going to be the next lecture. Okay, lecture 8 next week. All right. Okay, so now let's get into more detailed here. So it's just not just two examples here, and let's look at in general. Okay, how do we get? So we're gonna still focus on this portion here. Okay, still focus on this portion. Most probably actually focusing on this branch here. Okay, giving a z trans function, a pulse trans function. And how do we obtain a discrete space model? I'm going to show you a different type of a format here, okay? And okay, but first of all, let me introduce this idea, so-called simulation diagram. Yeah. So the state space model usually will be very easily derived once you have a simulation diagram, okay? But there are different ways of drawing simulation diagram, right? Yeah. So before we introduce the simulation diagram, and I want to introduce a simple so-called shift register. So you have x of k, and you have x of k plus 1, or you have x of k minus 1, right? So this is basically the sequence of numbers, okay? Sequence numbers. So if you remember, okay, let's say from x of k minus 1 to x of k, or the other way around, let's say from x of k to x of k minus 1. This is basically means what? You have one step of a delay here, right? One step of delay. So when you have one step of delay, so in general what we do is we can use a so-called shift register to represent this change in here. If this input is f of k and output is x of k minus 1, okay, and what we can do is when you look at the textbook, okay, people in general can use two different things to represent a shift register. One way is to use a q minus, okay, so they use a q minus to represent the shift register, okay, yeah. And the other way of representing is what you see usually is, as I use in this lecture, okay, is to use a z to the power negative 1. So that's actually quite easy to understand once we learned z transform, right? Okay, yeah. So we can use this one here, right? Yeah. The subtle difference is this. Okay, the subtle difference is why do people use a q? Because they kind of considering they're basically use a q to process this x of k, okay, x of k. They use a z in more rigorous manner the z doesn't operate on the k. The z operates on what? The capital X of z, right? The z transfer function. So when you operate this one here, what do you get? Right, you get this. Okay, so that's a little subtle difference, but that's okay, because as long as you know that what z to the power -1 does, all it does is to give you one step of shift, okay, or delay. Okay, that's enough. Okay, yeah. So then, if I have, okay, so how do I build up a simulation diagram? So it's kind of easy. Let's say if I have a difference equation. Let's say, for example, you have difference equation m of k equal to e of k minus e of k minus 1 minus m k minus 1. Okay, so let's say this is a difference equation here, right? Yeah. And I'm trying to derive this pulse transfer function. So one way of doing it is to take a z transport on both sides, and then you get the ratio between the input and output, right? That's basically what you do. Now, if I wanted to build the so-called simulation diagram, okay, and here's what happens next. So let's say I'm going to use this one here, okay, to build up this simulation diagram here. So if you look at the way that it goes here, there's e of k plus e of k minus 1. Now remember, this is input here, okay? So e of k is input. Then if this is the input here, okay, given one step of delay, okay, and you have e of k minus 1 here, right? So this is e of k, okay. Now, what this difference equation tells us is it's this e of k minus e of k minus 1. So basically, you can have a junction at here, okay, and both of them feeding into this junction addition point here. But it's this minus this, so it's going to be a negative. It's going to be a positive at here, okay, right? So then what comes out of this block at here, right? What comes out of the block will be this minus this. Okay, it's minus this. So it's not just this minus this, it's also minus this m of k minus 1 here, right? So there got to be m of k minus 1 at here, okay? M of k minus 1. So where's m of k minus 1 from? M of k minus 1 from m of k here, right? From m of k. And what's m of k? M of k is the output of this junction here, right? So basically this is of m of k here, right? This is m of k. And then you can see now, okay, where's my m of k? Where's my m of k, k minus 1 from? It comes from one step of delay, right? Based on m of k here, right? M of k. So overall, so this is the output, right? This is the simulation diagram, okay? Okay, this is a simulation diagram. Yeah. The state space model will be very easily derived based on the state space, based on the simulation diagram. All right. Yeah. So, but we need to know how to build a simulation diagram first. Okay. Yeah. Was that okay? Yeah. On the side here, usually it's also easy. Once you have a simulation diagram, I mean, simulation diagram is actually no difference from your block diagram in continuous system, right? Its block diagram is also a part of simulation diagram. But simulation diagram breaks down into the fundamental, into the very, very, very small elements in terms of z to the power -1, all right? Yeah. Block diagram is you have a box, and in the box, it's an S function, right? So it's not breaking down to the details. Yeah. So this is breaking down to the details here. So if I wanted to get the pulse transfer function here, you can use block diagram simplification technique, right, to derive this pulse transfer function. All right. Yeah. Okay. So now let's look at simulation diagram for more general case here. Okay, for more general case. And I'm going to give you as writing down here. So I'm going to give you a more general expression, but I'll go over examples. Okay. Using some simple ones here. Okay. So now let's consider. Okay, let's consider a g of z, okay, a pulse transfer function. Okay, let's consider a g of y of z over u of z equal to this pulse transfer function. Okay, so you have a numerator, you have a denominator. So then the numerator here, this is m, and denominator here is n. Okay, yeah, here's n. And usually the n is greater and equal to m. Okay, so I think in the previous lecture I mentioned one thing, a couple of things as to why n is greater or equal to m here, right? Yeah, but I'll give you an example. I'll explain in a little bit of detail here. So this is like a numerator over denominator. Okay, not s, z. Okay, denominator. Okay, and in other words, the degree of this numerator is m, and degree of this denominator is n. Okay, n here. Okay. The way of why we write this pulse transfer function in this format, right? Basically in the format of z to the power negative something, okay, negative power, negative number, okay, it's for the purpose of this simulation, building the simulation diagram here, okay. If you recall in the previous lecture, remember what I call this is usually used in the DSP format, right? Digital signal processing. So actually, when you design a digital filter, in the digital filter class you learn, you probably have a saying of you design a digital filter. How do you build up the digital filter, right? So there are different ways of building a digital filter. The way to build a digital filter is based on a z to the power -1 block, right? Okay. Yeah. So now what I'm gonna do is I'm gonna use a simple, not this one here to illustrate this this example here, okay? But if you prefer, okay, if you feel a little bit strange to this format, you can always write this back, okay, to the traditional, to the old format. So what you do is you basically multiply, okay, multiply this denominator and numerator with z to the power -n. With z to the power of n. Okay, yeah. So then the top one will become, the bottom one will become a0 zn plus a1, right? Zn minus 1 up to an like this, right? Yeah, up to a. And the top one will be b0 z and n, okay? And then plus until bm and zn minus n. Okay. So that'll become like this, right? Okay, yeah. Okay, so now the whole question here is how do I build up a simulation diagram here? So this is what's going to happen here. I said there are different ways of building the simulation diagram, so I'll show you one way of building the simulation diagram here. Okay, yeah. So, but I'm gonna use an example to show you here. Instead of this is because there are too many symbols got involved here, right? It's a little bit. So in the lecture notes, I did it, okay, based on the general thing set it here, okay? It's a general thing, but I'm going to use an example here, okay, to build. So let's say I have a g of z, okay, equal to 0.5z squared plus z, okay, over z cubed okay. So let's say this is my pulse transfer function. Okay. So if I compare the one with the general one that I just presented here, okay. So what is the degree of this denominator here? which is what, 3, right? And degree of this numerator, which is 2. Was it? It's 2, right? Yeah. So if you don't like this format, I mean, actually, what we're going to use is we're going to use the other format. So we can rewrite that. Okay. Okay. So basically, what we do is we divide, okay, both the numerator and denominator by z to the power of 3, right? By z to the power of 3. Okay. So the top one becomes 0.5 z negative 1 plus z negative 2. Bottom one here is 1 plus 0.6 negative 1, 0.5 z negative 2, 0.3 negative 3. Okay? Yeah. Is that okay? Yeah. Okay, so if I look at this one here, okay, if I basically in the future, I don't need you to go over the steps I'm going over today. In the future, what you're going to do is basically you can always always looking at the specific case you're dealing with a general formula there, right? Find the corresponding coefficients, okay? And then you can just use the formula, the final results, right? So if I compare this with that, right? This with that, and let's say what would I call this one here? Basically, in my particular case, what is A naught? A naught will be this number here, right? A naught. Okay. Yeah. This will be A1, A2, A3. Okay. Yeah. So we're looking at the numerator here, right? Looking at the numerator. So let's say what will be the B naught? Yeah. So B naught is actually 0 here, right? So, or you come back here, so B naught is a constant here, right? There's no constant, so B naught is 0. Okay. So then B1, that would be this term here. And B2, that would be this term. So B2 will be 1 in here, right? Will be 1. Okay? Yeah. So let's see, the B2, yeah. So in general, you can also have this, right? You can also have maybe z to the power negative 3. Is that good, right? Yeah. So that'll be B3 over here, but in this case, B3 will be 0, right? B3 is 0. Okay. Yeah. So this is what I need you to basically, at least in the future, is when you have one of this, okay, you can always get to know what's B now, B1, B2, B3, like this on to again here. Okay. Yeah. So you might argue is, so for some people who take modern control, or for some people who's taking some other lectures or some other things, some people use a slightly different symbols. Maybe probably they don't call it A naught here, they call it AN, A minus 1, like this, right? Yeah, so that's okay, okay? So if you taking that course, don't be confused saying, because they got different, but just because I'm using this is my standard here, okay? Not because it's wrong, right? Yeah, so it's just sort of standard way of writing it. Okay, so now let's do this one here. I'm gonna let this g of z, which is of course equal to u of z, y of z over u of z. Then I will introduce an intermediate function. Okay, introduce the intermediate one. Why is that? Because they cancel each other, right? I'm not changing the original one here. Okay, just introduce the intermediate one here. So that equal to my original numerator over denominator. Okay. Yeah. So this approach right here works on more and for general ones here, right? Yeah, not just the example. Okay, so then what this means is, so we're gonna let this y over z over h of z. Okay, so we're gonna let this y over z over h of z equal to the numerator So we're going to let this equal to the numerator. And in my particular case, the numerator is 0.5 z to the power negative 1 and z to the power negative 2, right? Okay. And then we're going to let this h of z over u of z equal to this 1 over d of z. Okay? Yeah, so nothing changed, just for the purpose of building this simulation diagram. Okay? So that'll give us what? That'll give us this 1 over 1 plus 0.6 . Okay, so that'll give us this guy here, right? Okay. All good? Right. This is pretty straightforward, right? So now, based on this first one here and the second one here, okay, so let's see what do I get. Based on this first one here, yeah, you know what, maybe I'll move it down the second one here. But you can write it right. Based on the first one here, what is my y of z? So y of z equal to this whole bunch multiplied by h of z, right? Yeah. Okay? So that basically is 0.5 z negative 1 h of z plus z negative 2 h of z. Okay? Remember what a y of z is. Actually, what's the y of z? Output, right? And what's u of z? It's input. Okay? Yeah. So h of z is just some intermediate things. What is h of z? We don't know. We don't really care. So over here, okay, we do a similar stuff over here. So let's see now. This time h of z. Okay. So I'm going to simplify this a little bit. So basically, this whole bunch, right? The bottom here multiplied by h of z equal to u of z, right? Okay. And I'll just single out this h of z by itself over here and move this whole bunch by h of z to the same side as u of z. All right. So then what do I get is I got u of z minus 0.6 . Is that clear? Yeah. There's nothing tricky here, just moving around the stuff, right? Okay. Yeah. Pardon me? Did I forget a 1? No, this 1 multiplied by h of z stays here, right? And this h of z by this 3 are moved to the same side of u of z as this one here, right? It's like a, yeah. Good? Yeah. Okay, good. Okay, so now the simulation diagram basically will be built based on these two here, right? Based on these two. Okay. So here's what we're going to draw it here. So we're going to draw the simulation diagram based on these two equations here. First for input, it's over here, right? Input is over here. Okay. Yeah. But let's build it. Let's build a thing based on h of z. So let's say suppose this is my h of z at here. Okay, this is h of z. Then for the based on the first one here, and I can obtain my y of z, right, based on this one here. Okay, based on this one here. And but maybe I'll try to obtain the second one here. Second one, try the second one here. So what's the second one here? So looking at this guy here, okay. So h of z by what? By z negative 1, right? And then multiply by negative 0.6, right? Multiply by negative 0.6. So if I don't put a negative 0.6, let's see if I put 0.6 here, okay, right? If I put 0.6 here, it's okay, right? So what's coming out of here is what? It's 0.6 negative 1 h of z, right? H of z. And we're going to use this quantity. This is 0.6 z negative 1 h of z. So we're going to use this quantity and this quantity add them together, but it's not added. It's this quantity minus this quantity, right? So we have a big box here, okay? And instead of positive, this is positive, and this is going to be a negative here, right? Negative. Okay. Is that good? Okay. I think there's a middle mistake here. This is a -2 here, right? This is -2 here. Okay. Yeah. Because here is 0.5 z to the power -2. Is that good? Yeah. So let's keep going. And for the second one here, this is 0.5 z -2. So z -2 basically that's z -1, -1 h over z, right? H over z here. Okay. And what is out of here? This is z -1 h over z, right? So we can just simply add another shifting block at here. And the output of this shifting block, right, it's z -2 h of z. Okay. Yeah. And this quantity, okay, by 0.5 at here, right? 0.5. Okay. Feed it back here, and same thing as a negative. So that'll be this quantity here, right? That'll be this quantity. So similarly, keep going. One more. And 0.3. Feed it back. Okay. So this portion, right? Realize this portion, right? Yeah. Is that good? Yeah. Okay, so then we just done a little bit here. So then we can construct this expression here, right? This expression. So what's this expression? This expression is 0.5 multiplied by which one? By the signal from here, right? The signal from here. And so you basically drag a term here, 0.5, right? 0.5. Okay. And the other one is z -2 each of us, so there should be a 1 out of this here. And the gain is 1, right? The gain is 1. And these two together, okay, give it to a block, okay? And the output of this block is y of z. And both on the positive here.
Dr. Chow?
Yeah.
If your gain is 1,
yeah.
you don't actually gain the gain.
You don't. Yeah, you can just drag through here. Yeah. Okay. So that's the simulation diagram based on this approach at here. Was that good? Yeah. Okay. So just for your exercise at here, okay, let's say I have a slightly different pulse transfer function, right? So you see this is my original pulse transfer function here, right? This is my original pulse transfer function. So let's see if I give you a pulse transfer function of this, okay? Let's see if the pulse transfer function is 0.5 z squared plus z. Okay, so this is the original one here, right? Let's see, I'm not going to change the bottom. I will just, I will change the numerator slightly. So this is the original one here, right? This is the original one here. So if I change the numerator here into 2, okay, so I added a term at here, okay? I added a term. So how would you modify this simulation diagram? What do you need to do to change this?
In the last one, you have gain of 2 and
That's right. So you're gonna do what? You could, well, I guess for some people who's not quite familiar, then you do the same thing, basically transform everything, right? Right? So you get this term here, right? 2z to the power negative 3. Okay, 2z to the power negative 3. Okay. And what does this, did I do right? Yeah. So 2z to the power negative 3. And where is that going to be added here? That's going to be added to here, right? Is that clear? Yeah. So basically, based on this one here, where is that z to the power? So what's coming out of here? This is z to the power 3 h of z, right? H of z. So we're going to just simply move in here and go like this. Okay? Yeah. Is that clear? Okay. So if I change that again, change that slightly again. Okay. If I let's say if I have 0.4, okay, plus z to the power 3 at here. Okay. So that'll be 0.4 over here, right? 0.4 over here. Then, based on this diagram, where should I add additional block?
H of z.
H of z. Where would you draw it? Here?
No, yeah, before the
Yeah, that's right. And here is 0.4. Okay? Yeah. Is that clear? Yeah. So, but what's the change in here, right? You look at this one. You look at the change. Look at the final one with the black one here. What would be the What would be the degree of the denominator here? The degree will be the same as, right? Yeah. So this 0.4, if I going back to the original one here, that 0.4 will be this number b0, right? B0 here. Okay. Yeah. And that m, if the same degree, right, basically will be the same as n here. Okay. Yeah. Good. Okay. So now we got this simulation diagram here, right? Let's go simulation diagram, and let's derive the state space equation based on the simulation diagram, right? Yeah, it's a little messy because I got two things inserted here. So let's consider to derive this state space equation based on the original one here. Okay, no 2, no 0.3, no 0.4. Okay, yeah. So what we're gonna do is, okay, we're gonna derive the state space equation based on the simulation diagram, not a difference equation. So then here's one way of doing it. Okay, yeah. So you know what? I'll erase this portion in here temporarily. Okay, is that okay? Yeah. Yeah. So good thing is I'm recording it, so if you're gonna watch it, you have the evidence that's there. Okay. So deriving state space equation require you to define a set of state variables, right? A set of state variables. So how do we define the state variables? And this is actually the advantage of simulation diagram. You can always, okay, so the rule of thumb is you can always define your state variables as the signal right out of this, right after each one of the register at here. Alright? Yeah. See, this is the delay register. Yeah, by the way, actually, if I wanted to realize this simulation diagram using circuits, right? Yeah. So each one of them basically behaves as a register. Okay, so you have a register. Each register will be used to store temporarily the signal, right? Yeah, and it'll be basically it'll behave like a delay there, right? Delay. Okay, yeah. So I'll write it down here. Okay. State variables. Okay. So it can be picked as the signal, okay, after each shift register. Okay, shift register. So what is state variable? State variable is x of k, right? X of k, so vector. Okay. Depends on the order of the system, then you have to have this same number of state variables here. So in my case, my order is 3, so I'm going to pick 3, right? So how many states, how many registers? 1, 2, 3. See that? Yeah. So we're going to do this. I'm going to pick this x1 of k at here. Okay, use the red color. So I'm going to pick, this is x1 of k, right? Yeah. And outside here will be x2 of k. Okay. And over here will be x3 of k. Is that clear? Right? Yeah. So that's the 3 state variables. Okay. Okay, so just the 3 state variable won't give you the state equation. So we have to get, the state equation is what? The state space equation is a relationship between k plus 1 and a k, right? And also this u of k. So now if I come back here, this is x1 of k here, right? And what should be before this guy here? This is 1 step delay, so this is x of the q, that's x2 of k, but at the same time, this is also what? The signal at here. The signal at here at the same time is also x what? This is x1 of k, so at the same time this is what? Exactly. Yeah, x1 of k plus 1, right? Yeah. At the same time, excuse me, over here is x2 k plus 1. Okay? Yeah. At the same time, over here, that's actually using it. So x3 k plus 1, right? Okay, so now you have the location of x3 of k plus 1, you have the location of so you have the location of x of k plus 1, you have the location of x of k. So we're ready to derive the state space equation. Okay? Yeah. So based on the simple observation, your objective is, right, to derive x of k plus 1 at here, right, and express all of them in terms of x of k, right? In terms of k. So that's actually pretty easy. So what is x1 of k? How x1 of k is related to what? Okay, right? Yeah. So that basically just x2 of k at here. Okay? x2 of k. And x2 of k plus 1 only related to x3 of k. So basically that's just x3 of k here, right? x3 of k. Okay. x3 of k, that's a bit of a tricky. So x3 of k, coming back here, where's the x3 of k? x3 of k is a signal out of this junction here, right? So which means x3 of k will equal to this guy minus this. Okay? Yeah. So what's this? It's this signal here is 0.6 z negative 1. Actually, not h of sz anymore. It's what was it? No. This signal here is this signal here is 0.6 x3 of k. Right? So this signal here is 0.6 x3 of k. right? And this signal here is 0.5 x2 of k. So we're using the state variables, right? And this signal here is 0.3 x1 of k. Okay, and this input is u of k, right? It's u of k. Okay, single input, so just one there. So now you use a simple subtraction and addition. Then x3 will be negative 0.3 x1 of k minus 0.5 x2 of k minus 0.6 x3 of k, and then plus the u of k. Is that good? Yeah. So this is the state equation, right? This is the state equation. Okay, this is state equation. So it's an equation describing the states, the state variables. Okay. If I write it in the matrix format, so I'll probably just use x of k plus 1 in here. Okay. Yeah, in matrix format. So what was it here? Is what? 0, right? 1, 0. Second row, 0, 0, what? 1. And third row, okay, could be this.
Don't you always have to add u of k?
Yes, of course, yes, yes. So in the end, u of k. So three things here will be 0, 0, 1. Yeah. Okay. Yeah. So that's a state variable. And then we also need the output, right? We also need the output here. So what's my output? Coming back to the simulation diagram, output is here, right? This is y of k. Okay. So y of k will be, this is 0.5 x2, no, x3, right? x3 of k. And this is x2 of k. So output is basically this plus this, right? This plus this. Okay. And that's this x2 of k plus 0.5 x3 of k. Okay. And in matrix format, okay, so the coefficient for the x1 of k here is 0, 1, 0.5. Right, so that's it. That's the state space model for that, based on that pulse transfer function. And here's your A matrix, here's your B, here's your C matrix, right? You don't have the D there. The reason is because the degree of the numerator is less than the degree of the denominator. All right? Yeah. Okay. So that's sort of a rough idea of getting simulation diagram and then getting the state space model, right? Yeah. Now let me just kind of elaborate a little bit about this the degree things of the numerator and denominator here, right? Yeah. So another S. I'm thinking about S here. Okay. So if you have this one here, I'll give you the conclusion first. Okay. When degree of this n is less than equal to degree of this d, okay, and what we see, this is so-called proper. Okay, the proper transfer function, the proper system. If degree of this is less than this, is called strictly proper. Okay, strictly proper. Yeah.
What do you mean by that?
That's right. So I'll explain what do I mean by proper or strictly proper. Okay. Yeah. Okay, we're finished writing here. So what I mean by this is this. The origin is basically a purely mathematical meaning definition there. Okay, so they deal with the polynomials. You have a polynomial here and there, you know, right? But when it comes to control system, okay, let's see if I use the example I have over here. Okay, if I use the example I have here. So what do I have here? I have a 0.5z. So let me just. Okay, I have a 0.5z squared plus z over okay, so I have this one here, and this is y of z over u of z here, right? It's this. So can you write this back into the difference equation format? Okay, write this one back into difference equation. So essentially, maybe you should write it everything, okay, in a delete format here, right? Delete format. And then in difference equation, what am I gonna get? I'm gonna get y of k. See, y of z multiplied that is y of k here, right? So maybe I use small y here. Is that right? Yeah. And this number multiplied by 0.6z negative 1. So you get 0.6 y of k minus 1, right? So, but I can move that to here. Is that good? Right? Yeah. And up to, you know, there's negative 3 k minus 3. Okay, so just see that. And the other side, here what you get here is what? 0.5 u of what? K minus 1. And u k minus 2. Is that clear? Yeah. So this is your output, right? This is your output. This is your input. Okay? So if you look at the relationship right here, what does the current output depend on? Exactly, right? See, it depends on the past output and what? The past input. So what do we call this kind of system? Proper system. It's actually strict proper. So this is actually so-called causal system, right? So your system current output depends only on the past input and the past output values. Is that clear? So current output, okay, depends on only past, okay, in this particular case, only past outputs and inputs, input values, rather, you know what I'm saying. So output values or input values, right? Yeah. So that's basically a causal system. Okay, that's a causal system. And this is why it calls strictly proper system. Okay, strictly proper. So then what happens? What happened if I have, right? What happened if I have? Remember what did I add there? I added the 0.4 here, right? So what happened if I added a 0.4z, basically, not here, basically 0.4z cubed here, and this is 0.4 plus z here, right? Yeah. So if I added a 0.4 here, then what am I gonna get here? I will get what? 0.4 what? U of k. Okay, you have k here. So when I add it here, according to my definition, this is so-called a proper knot, right? A proper knot. And from the difference point of view, this is what it looks like. So then, what does the current output depends on? Depends on the past output plus what? Plus present inputs, right? Present inputs. So the system, in other words, you give me a 3 volts input, the output immediately feels that, right? Immediately feels that. So that's the output has an immediate response to the input. You see that, right? But without this term here, without this term, you give me the input, the system is the output of system. There's always a 1-step delay, right? Corresponding to the input. You see the difference out here, right? Yeah. As a matter of fact, that's actually more practical. You know, basically, usually the system doesn't have this capability of having this immediate response to the input. So generally, it has this 1-step delay, right? You know, you're putting a 3 volts here, you know, with 0 order with all the other things, you know. There's going to be a 1-step delay, the response. The response will be 1-step delayed from this input. And if the system has multiple delays, you know, not just 1-step delay, maybe the system has 2-step delays, 3-step, who knows. So it's not going to be just -1 here. It's going to be -3 or 4 or 5, who knows, right? Yeah, okay. So that's the difference right here, right? That's the difference, okay? Yeah. But when I add this 0.4, that's 3 here. It's still a causal though, you know. So even though not just depending on the past now, it's also depending on the current, right? That's still a causal system. Okay, still a causal system. So what happened if here you add another 1.6 Z5 here? So basically the degree of the numerators is higher than the degree of the denominator now, right? Then here you would have what? A UK plus 1 term here, right? UK plus 1. So that then the current output is actually depends on the future inputs. So that's going to be what? A non-causal system. Okay? Yeah.
Can this happen in the real world? I mean,
no, non-causal won't happen. Yeah. Okay? Yeah. Okay, so that's basically the idea here, right? That's basically the idea. Was that good? Yeah. Now let's come back to this simulation diagram and state space equation right here. Okay. Yeah. And I want you to practice yourself right here. Okay. Remember what I said? I said you define the state variable as a signal out of this shift direct register. And I define this as x1 of k, x2 of k, and x3 of k, right? Now what if I define this as not x1 of k? What if I reverse the order here? Okay, reverse the order. Basically, I'll put this as x3, this is still x2, but this is x1. Is that okay, right? That's doable, right? Yeah, no, basically that's still satisfy the rule I was just saying there. That good, right? Yeah. But what are you going to get for the state space equation? You should expect you're not going to get exactly the same thing anymore, right? So things are going to change here, right? Things are going to change. Okay? Yeah. So that's actually one of the reasons I was saying, you know, the state space model, it's not unique, right? Unique. So here's what I want you to do, okay? So for this simple one here, practice, okay? Practice by defining the state variable with reversed order. Okay, with reverse order. And in my lecture notes, I did that, okay, for a much more general situation. And here, this is basically the reversed order, right? So in the simplified case, it's x3, it's x1 there, right? So I reverse order xn and x1 up to here, okay? Yeah. You end up with a totally different state space model, which basically does non-zero rows flip to the top, right? Okay, yeah. And what I need you to basically to know that in the future is, okay, you need to know where this is from, and given that Z transfer function, you can make use of this final results that are here, okay, to derive your state space model. Okay, yeah. So just make use of this. This will be fine. Was that okay? Yeah. Okay. So one more word is what was derived here. It's called control canonical form. Okay. The way that we derive this approach, okay, so this approach drawing simulation diagram and this approach of defining this state space state variables, we end up with a state space model, and the matrix that here is so-called control canonical form. We'll learn what the control canonical form is, but just remember right now, okay, the way we did all of this the process give us a so-called control canonical form. Okay, yeah. Okay. So that deals with the control canonical form. And there's no there is some other ways of basically deriving this state space model. Okay. The second way of deriving the state space model is this. Okay. Okay, I'm gonna write down here. It's so-called. We're gonna have so-called observable. Okay. Canonical form. Okay. Observable canonical form. I'm going to skip some steps here of how this is formed, derived here, but I will give you some information to look at it in the text. It's just going to take a lot of time to draw everything here. So take a look at this A-5-2 in textbook. Okay, take a look at this guy in a textbook regarding the derivation of this observable canonical form here, right? Yeah. So in short, okay, the if I do this, if I let AC, okay, BC and CC, okay, and D, okay, as the system matrices, okay, for this control canonical form. Okay, yeah. So I'll define ACC subscript C here represent this control canonical form here. So just like this matrix set here. This is AC, this is BC, this is CC. All right. Yeah. Okay. Then based on the derivation here, okay, so then this, I will let AO, BO, okay, and CO, okay, and then D as the system matrices for observable, Okay, canonical form. Okay. Canonical basically means the standard form. Okay, standard form. Then the relationship between these two is the AO, okay, equal to the transpose of this AC, and this BO equal to the transpose of CC, and the CC is the transpose of the BC, and D is not changing. Okay, D is still the same D. Oh yeah, CO. That's right. Thank you. Okay, so that'll be the results for observable ones here. Okay, that'll be observable ones. So, for example, just give me 1 second here. Right? 1 second. The simulation diagram, where did that go? Yeah, so for example, if I base on the previous example here, okay? So this is the state space model obtained for a control canonical format. And if I ask you is, can you derive an observable canonical form? So then what you can do is, right, you can simply write down, okay, by using this relationship here, okay, this relationship. So what is the transpose of AC? So transpose of AC is 0, 1, 0 here, 0, 0, 1 here, and -3 here, -0.5 here, -0.6 here. Okay, right? So if I go back here, was that right? So the transpose of this guy, right? Transpose this, 1 comes here, 1 comes here, those comes to here, right? From here. That's this AO here. Okay? Yeah. And plus BO. BO is a transpose of CC. CC here is it's this, right? Transpose this becomes 0, 1, 0.5. And Y is transpose BC. So 0, 0, 1 here, x of k. So this is the observable canonical form. Okay, observable canonical form. And the later lecture will explain why this is observable canonical form. Right? Yeah. So observable, as long as you can basically write the state space equation into an observable canonical form, and that basically the system saying is the system is observable. Right? Yeah. The concept will explain that later. Okay. So this portion here, right, give us the so-called observable. Now, this in terms of simulation diagram, okay, in terms of simulation diagram here, I'll draw it out. You can also build a simulation diagram based on this guy here, okay, based on this. So that what that's gonna give us is actually you can simply look at this one here. So you see, so what was that? Yeah, so y of k equal to 0, 0, 1 x of k. So basically meaning this is what? x3 of k here, right? Just x3 of k. Is that good? Right? So then if I build up a simulation diagram, this is going to happen here. Okay? I'll draw a couple of this z block right here. Okay, I draw a couple of Z block. Okay. Then we are defining, remember we're defining what? We're defining, okay, each of the Z block here, the output of each of Z block as, okay, the state variables. So we're going to define this as x3 of k. and this is going to be defined as x2 of k here, and this is going to be x1 of k here, right? x1 of k. Yeah. So this is your basically your y of k here. Yeah, this is your y of k. Okay. And what's in front of this x3 of k is x3 of k plus 1. Okay, 3 plus 1. Okay. So we're actually going to have a junction box here. Okay. And then I'll draw it out here. Just finish this thing, and then we'll explain here. Yeah, because I didn't go into details here, so let me maybe just draw it out here. So this simulation diagram is not in the lecture notes, and okay, that's the bottom here. This is U of k. Yeah, so this is the simulation diagram. Okay, this is a simulation diagram for the observable canonical form here. Okay, observable canonical form. So we can verify. Let's see if we can verify if they satisfy the state space equation here. Okay, state space equation. This is x3, and this is x2. And this is x1 here, right? It's x1. Okay, x1. Yeah. So what do we have here? At x1, before x1, this is x1 of k plus 1. Right? From k plus 1. What does x1 k plus 1 equal to? X k plus 1 equal to basically this signal here, right? This signal. Okay, this signal. So this signal is a negative 0.3 by x3 of k. Right? See that? So x1 of k plus 1 equal to x3 of k by negative 0.3. See this state space equation here? x1 of k equal to what? This number by x3 of k. Matrix multiplication, right? So maybe let me write here. All right? Yeah. For purpose trying to verify this. Okay? Yeah. So this satisfies this one here. What about this here? This is x2 of k plus 1, right? x2 of k plus 1. So x2 of k plus 1 will equal to this signal x3 again. Where's x2? x2 is here, right? It's a little bit embedded things. So based on here, see x2 of k is x1 minus 0.5 x3 plus u of k. Does that make sense, right? See x2 equal to what? Equal to x1, see, right? Plus, oh, not plus, minus 0.5 by negative 3 and plus u of k here, right? Okay, yeah. And then x3, which is this one here, similarly, right? It's x2 minus 0.6 x3 plus 0.5 u of k. So this simulation diagram describes the state space equation over here, right? Yeah. That's observable format here. Yeah. So when you're building a digital filter here, so this is actually one way of building a digital filter, right? Yeah. Okay. Yeah. The other one is also the other way. Any questions? So take a look at this lecture, the textbook example as the detailed derivation of observable one. I have 2 documents uploaded for this lecture, right? They are basically one document is summary on the control canonical and observable canonical. Those are basically the two main canonical form that we're going to use in this lecture. So there are 2 different standard control canonical form. The 2 different standards, it basically depends on how you define your state variables, right? Yeah. So if you reverse order, you got 2 different ones. Same thing for the observable ones. Okay, for those observable, there are also 2 different ones here. This is the this is observable one. Okay, so this is one standard format. Okay, yeah. The standard format is for a transfer function of this guy here, right? This guy here. Yeah. So you can in the future you can just simply grab the results and fit into your format, right? And the other one of the observable maybe look like this. It's the same idea. Basically, it depends on how you reverse order of the states, right? Yeah. Okay, so that's basically the two important formats that we're going to cover here. I do have one more here, which is called Jordan canonical form, and I guess we probably don't have the time to do this anymore. But I'll go over one more example, and then I'll talk about the MATLAB, how you implement that in the next lecture. Okay. So in MATLAB, MATLAB has a command called C2. Let me see, what is C2D? C2D, right? Yeah. MATLAB has a command called C2D. So in MATLAB, when you use the C2D, we actually use the C2D, right? You know, you have a transfer function, and then you have some zero order hold like that, right? Yeah. In MATLAB, when you also use C2D, you can also use C2D. Just give me 1 second. Let me just confirm there. Sorry, not the C2D. It's this TF to SS here. This command here. It's TF to SS. So in this command here, what you do is you punch in the numerator and denominator for the continuous block, right? From the continuous block, and then you give this sampling time here, and it'll give you a set of ABCDs, right? Give you a set of ABCD. Basically, you discretize this numerator block here into the ABCD. Actually, sorry, it's a little bit harder here. The numerator, the numerator denominator basically is the G of Z there, right? The numerator and the denominator. Okay, yeah, so that numerator denominator. So the MATLAB does this translation from Z pulse transfer function to a state space ABCD. Okay. Now, but you got to be careful here is what the MATLAB give the ABCD give you. It give you a control canonical form. Okay, it give you a control canonical form. Okay, it's actually a slightly different control canonical form sometimes. So if you hand derivation different from the MATLAB results, don't panic, right? Yeah. It doesn't necessarily means you didn't do right. Okay, just because the state space model is not unique. Okay, yeah. Is that good? Yeah. So I'll go over a little bit details in the next lecture, and then we'll move on. Okay. Yeah. Okay.